Hello everyone. Hello everyone. Welcome to this live session of course Renewable Energy Engineering, Solar, Wind and Biomass Energy System. So as you know, this live session is mainly to clarify few queries or the doubts regarding the course and its content. So if you have any doubt or the query, so you can raise or maybe you can type in the chat box here. Because there was one query online in the Excel sheet I could see here related to the monthly average hourly radiation for the flat plate collector. So I think for this calculation, detailed explanation has already been given in the previous live session, as well as the detailed calculation part is already covered in one of the assignment. So I still suggest you to kindly go through that particular part to know about this calculation of hourly radiation. This is part was discussed in the previous live session as well. So there is a second query regarding the difference between the hydropyrolysis and the hydrous pyrolysis and the amount of carbon yield here. So now suppose if we discuss about the hydropyrolysis and the hydrous pyrolysis, so there is a slight difference between these two processes. In fact, the hydropyrolysis, in the sense, this particular process is carried out in presence of some high pressure hydrogen. That's why it is called as a hydro, means the hydrogen is being used for the pyrolysis process, or you can say during the pyrolysis process. And here the purpose is like to increase the volatile yield, because by doing that we are increasing the volatile yield, so that may convert it into a bio oil. So proportion of the low molecular mass hydrocarbon also gets increase in this case of the you can say hydropyrolysis process. And it is basically a process which can produce the bio oil with reduced oxygen as well, because what happen in this case is like when the hydrogen is there, so this hydrogen gets combined with the oxygen which is present there, and it forms the water molecule. So as a result, the oxygen is getting consumed inside the process itself, and hence the bio oil oxygen content gets reduced in case of this hydropyrolysis process. That is a major advantage of this particular process. And now suppose if you go for this hydrous pyrolysis, so hydrous in the sense is like it is carried out in the presence of high temperature of water. So water is the medium which is used during this hydrous pyrolysis process, and this particular process also tries to convert the entire material into a required product. And in this case, what happens is like, for example, in the pyrolysis process, there are two stages, like the primary cracking and the secondary cracking. That is called as the primary stage and the secondary stage. So in this process, so the second stage in which the hydrocarbon is cracked into a lighter hydrocarbon compound further, and but there the temperature requirement is slightly high. It goes up to right around 480 to 500 degree Celsius. And in this case, but it's not specific that the oxygen content is decreasing in this particular case of hydrous pyrolysis, because here the hydrogen is not present, so as a result it is not getting converted into a water molecule. But then there will be a certain high oxygen content will be present in case of the hydrous pyrolysis process by oil, whereas when it's a hydro, when it is in presence of hydrogen, that oxygen content automatically get decreased because of the conversion of oxygen into the water. So that is important difference between these two process, and I hope this clarifies the doubt which was raised in the Excel sheet which I could see here. So regarding the problem number in the assignment number 7, or somebody is asking, actually I already made, I will just share with you the, because problem number 7 in the assignment 10, somebody is saying there is some query in that part. So in fact, the assignment 10 had actually 3 examples, I guess. Yes, 3 examples were there in the assignment, assignment 10. So the first example highlights actually the biomass gasifier, which is operating at around 180 kilogram per hour of the biomass, and the feeding rate is used to run the compression ignition engine. I am reading the statement, then I will let you know the solution for this also. And this engine has around 32% of the efficiency, and it operates in the dual fuel mode with or maybe let me share this screen with you so that you can see the slides also. I guess that will be better for you, so that you can also see the slides. So I guess the slides are visible to you now. So if you see these slides here, so this is what first example in the assignment 10. Here basically the thing is like we just need to calculate the gasifier efficiency. In the sense is like when you are replacing the fuel, that is a diesel, with the fuel obtained from the gasifier. Suppose that is a gas, which is majorly a hydrogen gas. So if you are replacing such fuel with the gasifier fuel, then we need to find out like the gasifier efficiency, how that particular gasifier is working, and what is the efficiency of that particular gasifier to produce that much amount of the energy from it. So now if you see here, the given quantities are like the biomass feeding rate is around 180 kg per hour, and then the biomass calorific value, which is mentioned here, it is 16 megajoule per kg, and power input to the gasifier, if you need to calculate. So this, suppose if you remember the assignment part, there I briefly described these particular terms, that is power input to the gasifier and the power output from the gasifier. So input to the gasifier in the sense is like when the biomass is getting fed inside the gasifier, that particular biomass is getting converted into a kind of a product. Okay. So now here we need to calculate for this specific feed rate of the biomass, what will be the power input which is required. Okay, so that means nothing but the what is the power input which is going inside the gasifier. So which is 180 kg per hour of the biomass feeding rate. So now these hours we are just trying to get converted into a second, so that once we have the kilojoule per second, we can convert those unit into a kilowatt, right? So here this is a simple conversion. Here is like hours we are just converting into a seconds here, and then we are just multiplying it by the calorific value, because calorific value is nothing but the heating value of this biomass. So once you multiply this, the kilogram will get cancelled, The hour will get cancelled. We'll get the kilojoule per second. This entire quantity in terms of kilojoule per second, that is a kilowatt. So this is basically the power input to the gasifier. Input in the sense, why we are saying it as an input, because you have to understand one thing here. We don't know what is exactly the input to the gasifier right now, because we only know the biomass input. So based on the biomass input, we are just converting that biomass input to a power input to the gasifier, because once we know the power input and the power output from the gasifier, we can calculate its efficiency, right? So here we have just converted that into a power input. So once we know this is the power input to the gasifier, then the energy which is produced by the gasifier engine system is per day is given as 17 to 80 megajoule, right? So now once we know this is the energy which is produced by the engine gasification system per day, so the power output from this engine need to be calculated, because we know the specific duration and the running time of this particular engine. So this is on the megajoule per day. So now we are just converting this unit into a kilowatt again, because we have to match with the unit here, right? So now once we multiply this quantity by in terms of day and again convert it into a seconds, we get in the form of this megawatt, right? And that we are converting into a kilowatt, because again this is coming in the form of the joules per second. Hour will get cancelled here, day will get cancelled, so we'll get megajoule per second, that is a megawatt. So we are converting that megawatt into a kilowatt here. And efficiency of the engine is already given here, that is the 32% efficiency. Now having these quantities, now we can calculate easily the gasifier efficiency, because the total power input to the engine was like power output is nothing but 200. So the efficiency of the engine was around 32%. So once you divide by the efficiency, so you'll come to know like what is the input power which was given into the engine, because the engine is working with only 32% efficiency. That means whatever the input is coming into the engine, only 32% is getting converted into a useful energy. Remaining is nothing but getting you can say as a waste in the form of the non efficiency of that particular engine. So once we divide it by 0.32, so this is basically the value which indicates the total power which is input to the engine. And once we input this much amount of power, because of the 32% efficiency, only 200 kilowatt amount of the output power is coming from the engine gasification system, right? So now given this, the engine operates in the dual fuel mode with 80% of the diesel replacement, as mentioned in the example. So that means the 80% of the total power supplied is from the gasifier. The replacement is like here, the 80% diesel replacement means 80% of the diesel is getting replaced here, right? So getting replaced by what is nothing but by the gasifier fuel. Okay. So now the power supplied from the gasifier is 0.8 into the total power input to the engine. So total power input to the engine is nothing but 625. So the 80% of that is nothing but 500 kilowatt. So the 500 kilowatt is the power which is contributed from the gasifier fuel. And the remaining, that is 625 minus 500, it gives you the power, or you can say the contribution from the diesel fuel, right? So summation of these two is nothing but the 625, that is equal to 100% of the fuel. And now once you know this quantity, you can easily calculate the gasifier efficiency, because this is the power output from the gasifier, right? So now the power output from the gasifier is this much, and the power input we have just calculated in the previous slide, that is around 800 kilowatt here, right? Power input to the gasifier. So if you divide these two quantities, output to the input, it gives this much amount of the efficiency. That means the gasifier efficiency is 62.5%. And this I already mentioned in one of the lecture, that the thermal gasification system is one of the such a system. It works with the highest conversion and with very good efficiency as well. Okay. So this is one of the example which we have actually given for the assignment. There is one more simple example from the assignment 10 only, which is related to just conversion of this molar composition to the weight fraction of the oxygen and the nitrogen gas. And this is related to process of the combustion of the fuel, if you remember this part carefully. So here the answer is like 0.23 and then 0.77. And now how this answer is reaching to this particular values, that will discuss here. Say for example, here if you see these moles is nothing but you have the weight by this molecular weight, right? So weight is nothing but in the form of the specific compound, like for example here oxygen and the nitrogen. So now if you see here, the this is we have represented in this form. Now if you have to convert this into a weight, so you have to multiply these moles into its molecular weight. So here we know the molar composition of the oxygen as 0.21. So weight of the oxygen is equal to molar percentage of the oxygen into its molecular weight, that is 32 gram per mole. Similarly for the nitrogen it is 0.79 into 28 gram per mole. If you multiply these two, we are converting these moles into a grams. Simple. Now when we say that we have to convert this in the form of the weight fraction of oxygen and in the nitrogen gas in the air, that means we have to convert this mole percentage into mole composition into a weight fraction now. So now we got the values of this component in the weight form, that is in the gram. So oxygen, if you have to calculate the weight fraction or the mass fraction of the oxygen, so it is 6.72, that is the oxygen mass divided by the total mass of air, that is oxygen and then the nitrogen. So that is nothing but summation of 6.72 plus 22.12. So if you do this division, you will get the value in the form of 0.23 here. And similarly for nitrogen, when it's a nitrogen, so the total nitrogen in the form of gram divided by the total composition of the gas, that is oxygen plus nitrogen. So it gives you a nitrogen weight fraction, or you can say the mass fraction in the gas. So that comes out to be around 0.77, and that is what, and this also we discussed in one of the lecture about this combustion part, where we mentioned that sometime if you are converting in the form of mass fraction, then you can easily convert using this simple concept. This is one of the simple example we actually gave for the assignment to solve, right? So I think that was the one example, or these two examples majorly we solved in the assignment 10. Actually, there is one question here I can see again, which is related to the calorific values of the gasifier product and the conventional fuels to be accounted when it is fed to the CI engine. So because say when it's a fuel in the engine, it is already in the form of the combination of the fuel, that is in the form of gasifier and in the diesel, right? So now in this case, the because once we have initiated the engine combustion process in the engine, so now the conventional and the gasifier product, as a reason we are replacing this diesel with the gasifier fuel. Okay, so now these two calorific values of the diesel as well as the you can say the gasifier fuel will compensate each other and will have the particular efficiency of the engine in the burning process, in the CI engine basically. Clear? Because now there we consider that as a kind of you can say a system where it is having a combination of both the fuels. And when it is in the combustion chamber, so now obviously because of these two different fuels, there is a calorific value difference is there. But then we are considering here is that the entire combustion is occurring inside the gas, you can say the CI engine system, and then based on that we have to consider the calorific value of the gas, because the major fuel here is now the gasifier, because 80% is getting replaced by the gasifier fuel. So because of that, the major fuel here is now the you can say the gasifier fuel. And since we have estimated the gasifier efficiency, so we are calculating the we are considering the calorific value of the biomass which is being used for the conversion process in the gasifier. Because we cannot consider the conventional fuel, that is the diesel fuel's calorific value during this calculation. The reason is like because we are specifying your calculation to find out the efficiency of the gasifier. Now, if you consider the conventional fuel calorific value, so obviously there will be a big change in the efficiency of the gasifier. Okay, so for that reason, we are just trying to align this with the gasifier efficiency as well as the fuel which is fed into the gasifier for the gasification process. So that calorific value we are considering for the efficiency calculation. Because if you consider the conventional fuel efficiency and calorific value again, so it will change drastically in that case. I can see one more question there, whether more carbon yield possible from hydrous or hydropyrolysis. So here carbon yield in the sense is it depends on the basically the kind of material which is being used for the pyrolysis process. If you're using like a kind of material like that is a rubber or tire, then obviously the there will be a shift pattern we can see in the pyrolysis process. Because if you try to stick it to the biomass material, then in that sense you can find out here that the carbon which is obtained here is of relatively better properties in terms of surface area. Also, if you see here, the surface area also found to be relatively higher in case of these processes. So there is one more query like regarding assignment 1 to 5 solution and the explanation required. So it's like we need to have the entire discussion of the assignment then only in this particular session. But these assignments were actually very simple if you try to follow the lectures. So all the assignments plan according to the lectures and the example discussed in the specific lecture. And if you just follow those particular examples properly I guess you won't find you won't guess you obvious sorry you won't find any difficulties while solving these examples in the assignment, I guess. But maybe if required then for the quick uh, go through, I can just start with the first 6 number assignment. But these are very simple. Actually, the example not very critical here, because if you see the first assignment where there was the one example which is related to the calculation of the you can say the weight fraction of the moisture content, that is on the weight basis and the dry basis. So for this, if you follow the initial lectures regarding the physical properties of the biomass material and how these particular properties affects the biomass actually the conversion as well, and how these are important in the defining the specific conversion process. So there actually the if you have to calculate the moisture content, that is on the weight fraction basis, on the weight basis I would say rather. So this is a very simple formula which need to be used for this purpose, and then you can calculate the uh, weight fraction, or you can say the moisture content on the weight basis. Similarly on the dry basis, because for the dry basis purpose, it is mentioned here the weight of the biomass before the moisture removal is this much. That means it is including the moisture in that. Okay, so that is including the moisture component in the system. So because of that, if you see here the weight fraction, or you can say the mass moisture fraction contained in the rice husk on the dry basis is around this much. So around like 50.49, and this is around like 0.62. So this is a simple example which we have asked to solve in the assignment. And there is another example was asked in the assignment number 6 again, that is like how to determine the percentage of fixed carbon of the biomass. So here specifically we targeted about the bamboo biomass, say for example on the dry and weight basis again. So here again it is on the similar example of the similar trend, but here there is a slight twist is there in this example because here the weight of the crucible is given as this much, and the difference in the initial and the final weight of the biomass after moisture removal is given as 0.36 gram. So this is basically the difference. Okay, so the difference between the initial and the final weight of the biomass after moisture removal. So now based on this, you can calculate the initial weight of the biomass. So how to do that? Because the initial weight of the biomass plus crucible is given as 24.83 and the crucible weight is given as this one. So now once you have these two value, you just subtract these two value, you will get the initial weight of the biomass. Simple, right? And once we know this is the initial weight of the biomass and the difference between the initial and the final weight of biomass is 0.36. So the formula itself is indicates that the difference divided by the initial, so that gives you the percentage moisture, that is 8.69%. It is as simple as that. Only here there is a slight twist, is like we have just indicated that the initial and the final weight of the biomass after moisture removal is this one, and that is the difference basically. And the volatile matter as well as the ash content, everything is given. So now based on this, if you have to just calculate the fixed carbon content, so there is a simple formula is given in the lecture as well. That is 100 minus the volatile matter plus ash content, because this is on the dry basis. So here we cannot account the moisture. Okay. So now similarly, if you have to calculate this is on the weight basis, then you can include the moisture content in the biomass. That is 100 minus moisture content plus volatile matter plus ash. That gives you the fixed carbon of the specific biomass on the weight basis. Clear? And there is another example which we asked to calculate in the assignment is nothing but the high reading value of the biomass. So for any specific biomass, we can calculate the high rating value. There is nothing specific about it. And then if provided the latent heat of vaporization of the water value is given, the percentage of the, you can say the moisture and the percentage of the hydrogen is given in the example, as well as the low reading value of the specific biomass is given in the example. So then you can easily calculate the high rating value, because you have to just simply replace the values in this equation, and you can convert this, you can just shift these terms, HHV on the left side and the LHV on this side, and then, or rather you can shift this entire term to this side, and then you will get the HHV value, which comes out to be around this much. So I don't see any difficulties in this example. If you are attending this example, I guess there is no such difficulty level. Similarly, the assignment number 7, it is a very simple example again been asked in the assignment to solve, because if you remember this component of the lecture about the biogas, there we have specifically mentioned about the CO2 yield as well as the you can say the gas yield for the different biomass system like fats, then for lipids, for carbohydrates. So it is given in the one specific table. So this example is in line with that particular table only. So here the amount of CO2 and the methane content in the 750 liter of the biogas generated by the fat based feedstock needs to be calculated. So here, suppose if you remember that particular table, then the CO2 and the methane content in the biogas from the fat specific feedstock is 33% and the 67%. So similarly, 33% of the 750 liter is nothing but 247.5. So that is the CO2. And 67% of the 750 is nothing but 502.5, that is the methane. So this is basically the answer to this particular question. And I hope actually this is very simple, and it clears your doubt also, like how to calculate these values. So instead of fat, there might be you can say the protein, there might be a carbohydrate value would be given. So those values for the specific component should be known to you, so that you can calculate these particular values on the proportionate basis of CO2 and the methane. Similarly, in the assignment 8, that is specific to this biogas processing only. So it was basically asked to calculate the volume, total volume of the manure which is required in the digester system for the farm, which is consisting of around like 75 cows. Okay, and then the dry manure produced per cow is given, as well as the dry matter percentage in the manure was given as 14%, and the density of the wet manure was given as 1080 kg per meter cube. Clear? So now, if you see the total number of cows here, it is given as 75, and the dry manure production per cow is given as 0.7. So now, with the help of these terms, as well as the retention time, which is 30 days, and the dry matter in the manure is 14%. So the total amount of the dry manure produced is calculated just by simply multiplying 0.7 into the 75, because the farm has 75 cows. It comes out to be around like 52.5 kgs of the dry manure. That is a per day basis. Okay. So now the total weight of wet manure is like how much? Because the dry manure is this much, and the percentage of dry matter in the manure is 14%. So that means you are just dividing it by the 14%, which is the dry matter content in the, because this is on the dry manure basis. Okay. So that's the reason we are dividing it by the 14%, so that you can get the exact manure, which is including the, you can say the liquid part, but I would not mention the liquid, but you can say the moist content of that particular manure. Okay, and then you can calculate the volume of the wet manure per day basis. So this is basically here, if you see, so mass of the wet manure, which is coming out 375, and then density, you know, kg per meter cube. So kg will get cancelled, and then accordingly you will get the value in the form of meter cube, that is 0.347 meter cube. So this is the volume of the wet manure now, not the dry, because we already converted that into a wet by dividing it by the dry matter percentage here. Okay. So the total volume is like 0.347 into 30 days. You multiply it by, you will get the total manure, which is total volume of the manure which is required is around this much. Clear? So this way actually this example was designed. So another example is also of the similar nature, and as we discussed about this gasifier efficiency system and how to calculate the gasifier efficiency, here it is on the biogas digester basis now. Okay, so here it was asked to in this example it was asked to calculate the net energy which is obtained from the biogas digester having a boiler efficiency of around like 35%. So it is basically the net energy which can be obtained from the specific gas which is obtained from the digester. So the efficiency is 35%. The heat of combustion per unit volume of the methane is given as 22 megajoule per meter cube. That is a calorific value. Volume of the biogas is given as 15 meter cube, and other value, that is nothing but 15 meter cube of methane in every 45 meter cube of the biogas. So this is one assumption that is given in the example to solve this specific example here. So now if you see here, so the fraction of the methane in the biogas, if you need, because it is mentioned that the volume of the biogas is around 15 meter cube. Okay, and 15 meter cube of methane in every 45 meter cube of biogas. So biogas indicates a mixture of CO2 plus methane plus small traces of the CO, hydrogen sulfide and other gases as well, right? So that is the composition of the biogas. But in that the methane is 15 meter cube. So the fraction is nothing but 15 by 45, that is equal to 0.33. This is very simple. So the net energy is nothing but now the boiler efficiency, you know the boiler efficiency 35%, volume of the biogas, you know 15 meter cube. Now you require here the fraction of methane which is present in the biogas, because we are just simply multiplying it by the volume of the biogas. That is not sufficient enough, because only the methane burning is contributing into the generating the energy, because the other gas is not contributing in producing the energy. Methane is nothing but the major fuel here, right? So that's the reason that fraction is required. Multiply by its combustion value. So you'll get the net energy is nothing but 38.46. So this is very simple. If you neglect this 0.33 and just you simply multiply this, your answer may not be the exact one, because then you are calculating the net energy from the entire biogas. Because the entire biogas is not taking part into the combustion. Only the methane fraction is taking part into the combustion. So the specific energy which is obtained, that's what is mentioned by in the example, is like the net energy which is obtained from the digester, not like the energy which is obtained from the digester. Net because of the only the combustion of the methane. So another example which is related to assignment 8 is about the calculation of the biogas which is produced in a plant for the output of around like 680 chickens which are there. If the gas formation rate from this manure is around 0.5 meter cube per kg, and the manure production rate is around this much. So this is very simple again, because we know the total numbers which are available. The production rate, you know, you just simply multiply it. Okay, you will get the total manure production that comes out to be around this much. And the gas formation we know is 0.5 meter cube per kg. So you have to simply multiply these two terms to get the total biogas which is produced from this particular source, which is around 20.4. So this is again a very simple example. And this is another very specific example which is given in the assignment 9. But this is also one of the very simple way of converting this sugar yield, you can say, or you can say the concentration of sugar. Okay, so because the theoretical ethanol yield from the C5 sugar is given as 314 kilogram per ton. Based on this, we need to calculate the approximate concentration of the sugars which are present in the biomass if the theoretical ethanol yield constant is 0.51, and ethanol density is always known as 0.789 gram per centimeter cube, but that is at 20 degrees C. Okay, so this data is sufficient enough to just calculate the approximate concentration of the sugar. Why? Because the theoretical ethanol yield is nothing but concentration of that particular sugar, as it is C5 sugar here, into the constant of theoretical ethanol yield, that is 0.51. Now this value we know, that is the theoretical ethanol yield is 314 kilogram per ton. This concentration we need to calculate because this constant also is given in the example, right? So you have to just simply rearrange this term, just convert these values, and you will get the concentration, because you have to just divide it by 0.51 here, you will get 615.69 kilogram per ton. Simple. Okay, so this is in kilogram per ton. If you have to convert into liter per ton, you simply divide it by the density there. And once you divide it by the density of the ethanol, so you will get the exact concentration of the sugar in liter per ton, which is around like 780. Simple. Okay, so this is also one of the simple example. And this assignment number 10 example, I guess I already discussed this now, just a few minutes before. Okay, so I hope this clarifies most of your doubts now regarding the assignment as well, and how to solve these assignment examples. Maybe you can practice this example if required again, because your examples in the question paper would be on the similar line with a slight again twist and changes in the statement of the examples. So I still suggest all of you just to try to go through once again to the assignment examples and try to solve it if you have done some mistakes while solving these assignments. So I could see there are no more queries actually in the online platform as well. Now is it okay? So it got muted automatically? Oh, so what I suggest is like you can. So it was from the beginning. It was muted or hello? It was muted from the beginning or just now. So I suggest all of you try to go through all those assignment examples once again and try to solve it one more time. Okay. So let us try to conclude this session here. And if you have any further doubts, you may reach to us. The email ID I have given at the end of my every lecture. So you can just mail me on that particular email address, or as we know, there is a question answer session is there after every week. So you can raise your queries there also. We'll try to answer all the to your queries to the most of your satisfaction. Okay, then we'll just stop here. And thank you all for joining for this live session on the renewable energy engineering, that is solar, wind, biomass energy system. So may I log off now from this meeting?